using BJT transistor. Here to do the feedback biasing, what we do is we connect a resistor between base and the collector. Okay, so let's mention that one right here. Biasing using collector to base feedback. And we do that by connecting a resistor between collector and the base. Connecting a resistor between collector and the base. Okay, in this video we're just going to analyze this circuit and derive the expression for the IB current and also the output voltage VCE and or the output current IC. Okay, now let's go ahead and see that. So first let's see each term. VCC is the source voltage and RC is the resistance in the collector, and there's a current flow through this, and you see the current flow through this one is IB, that's the base current, and the current flow through this one is the IC, that's collector current. And this current right here should be, according to KCL, this should be addition of these two, because if you look at the node right here, whatever the current entering the node should be the current equal to current exiting the node. So this one should be IB plus IC, and we have IB, that's base current, and then VBE is the base emitter voltage, VC is the collector emitter voltage, and RB is the feedback resistance, or you can say biasing resistance, and that is basically it. Okay, now let's apply KVL inside of this circuit. If I just draw the inside of the circuit, it's going to look like this. We are going to have the voltage source on top, VCC, and then we have the RC, and the current through this is IB plus IC, and then this one goes like this, and here we have RB resistance, and the current flow through here to here is IB current, and then it's going out, and this one is VBE, and then connected to the ground. This is emitter. Okay, if we apply KVL right here, KVL says addition of all the voltage is equal to 0. Then if we start from VCC, then this is going to be VCC minus this voltage, that is the current times the resistance. The current going through this is IB plus IC, so IB plus IC times the RC, and then minus RB times IB, or IB times RB, and then minus VBE. Okay, the whole thing should be equal to 0. Okay, now here we want to rearrange this one and bring in terms of IB, but before we do that, there are some things we can do it to make it simpler and better. One of the things we can do is, instead of IC, we can replace that one with beta IB, because IC is equal to beta IB, so we can do that. If we do that, then this is going to become VCC minus IB. Instead of IC, I'm going to replace them with beta IB times RC, and others remain the same, RB times IB minus VBE, that's equal to 0. The next thing we can do is we can take IB common. Okay, I'm going to go ahead and continue in the next page. So let's keep the other terms as it is. So this is going to be VCC, and then here we have IB plus beta IB. So here if I take IB common, okay, I'm taking the IB common, so it's going to be just 1 plus beta inside. Okay, and then we have RC right here, and after that we have RB times minus RB times IB, and then we have minus VB. That's equal to 0. Now what we can do is we can take the IB common again, because this too has IB common. So this is going to be VCC, and if I take IB common, this is going to be 1 plus beta times RC. Okay, and I took the negative also outside, so this negative will be removed, so this is going to be just plus right here, plus RB, and then minus VBE should be equal to 0. Now if we rearrange this one in terms of IB, this is going to look like this. IB is equal to VCC minus VBE divided by RB plus 1 plus beta times the RC. Okay, this is the IB equation. Now if you want to derive the equation for the VCE and IC, we have to look at the outside of the circuit. So we have to just cut the inside of the part and take this part alone, the outside part alone. And if we draw the circuit, it's going to look like this. Let me use a new page for it. So first we have a voltage source, that's VCC, and then we have a collector resistor, that's RC, and the current through this RC resistor is IC plus IB, and then this one goes through the BJT transistor, and here we have a voltage VCE, collector emitter voltage right here, and this one connected to the ground. Okay, and if you apply KVL right here, then this should be VCC minus IC plus IC plus IB times the resistance RC, and then minus VCE should be equal to 0. Here also we can do the same thing, like instead of IC we can replace that one with beta IB to make the less unknown terms. So if you do that, then this is going to be VCC minus beta IB plus IB, RC minus VCE should be equal to 0, and if you take IB common here, this is going to be 1 plus beta times RC minus VCE, that's equal to 0. Therefore, if we rearrange this one in terms of VCE, this is going to be VCE is equal to VCC minus IB times 1 plus beta times RC, and that is the expression for the VCE. For the IC, we can do the same thing, like now if I want to express in terms of IC, I have to keep the IC as it is. If I bring, okay, you know that, like instead of IC we replace, like let me look at the relations. IC is equal to beta times IB, so IB is equal to IC over beta. Okay, so what we can do is instead of IB we can replace that one with IC over beta, so that one looks more related to IC because we are trying to derive an expression for IC. So this is going to be VCC minus IC, and instead of IB I replace it with IC over beta times RC minus VCE should be equal to 0. Then if I take the IC common, then this is going to be VCC minus IC, and then 1 plus 1 over beta times RC minus VCE is equal to 0. And if I write this one in terms of IC, then IC is going to become VCC minus VCE divided by 1 plus 1 over beta times the RC, and that's the IC expression. And that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.